Okay, theoretically we should be recording. Say hi, Izzy.
Hi, Izzy.
She thinks that's boring and lame. I know. To start, I want you guys to now have committed to memory 2 of these 3, because the third one you can derive from the first 2. You need to know these 2. Let's make my box kind of actually fix that. Okay. And really with the first one, you just need to know, that was totally supposed to be a highlighter, you need to know this one right there, because you can derive the other 2 from that. Those are going to be completely essential, because in a couple of days here, well, actually months, we'll be integrating and we'll have to use the cosine double angle identity a lot, like a lot. You need, please trust me on this, you need to know these 2 and have them completely committed to memory. The thing about the second identity is that you can use that anytime you have sine times cosine of the same thing. You can kind of work it back around and make it a sine double angle identity, and that could be a lot easier to do a derivative of and an integral. But let's start. So the first example is going to be sort of the simplistic sense of when you have a product and the products are groups. So we've seen this before a little bit. We're going to do basic product rule on this. First times the derivative of the second, and the derivative of the second multiplies the derivative of the inner function, 2x minus 1. So that would be face 2, times the 3 times the 2x minus 5 squared. So all of that is first derivative of the second, plus, not minus, save minus for low d high minus high d low, plus the second times the derivative of the first. So a 2x minus 5 cubed times a 2 and an x, or a 2x. I don't really care how you put it, because our next step is going to deal with the factoring that's involved in that. So for those of you that I talked to today, I've told you that my preferred system is to check both of these, and underlining can sometimes help you see the 2 groups separated by the plus sign. Check constants first. You got 2's and 3's, and only a 2 can come out. Check your single variables, your little singletons there, your x's. Got an x there. And then just start going through your factors. There's only one factor that's present, it's a 2x minus 5, and the largest power that you have is a squared, which means that what's left over once you pull that out is a 3, an x, plus a single 2x minus 5, which I can write without parentheses because that can just be dropped. Now, if you can do just a little bit of anticipation, you can see that you can factor a 5 out of that, this thing right here. If I add the 3x and a 5x, I'm going to get a 5x minus 5. Let's just take a step and pull the 5 out now and make that become a 10x, 2x minus 5 squared. And this was 5x minus 5, with a 5 taken out is x minus 1. And then we'll keep our notation clean, still write an f prime of x in front of, and now we have a nice clean factored form of that. Okay? In a good factored form, what you should have noticed is that you have your powers, or your different, let's say your powers, your different factors are reduced by 1. Both of them are. And you have some extra stuff left over. Like, you know, you got some stuff that you dealt with, including that x minus 1. So that's common. Okay, number 2. Do not do low d high on anything that has a constant in the denominator and the numerator. I know if I wanted to mess you guys up, I could write this as x squared times 9 minus x squared over 2, and I'd watch you low d high that. Unnecessary. Don't need to. And not good to do. What is good to do is actually to group that off, and just to keep the 1/2 out all the way until the end. 1/2 times a function, we can just pull the 1/2 out and multiply the whole thing by 1/2 at the end. That's called the constant multiplier rule. The better thing to do is to treat this as a product and to actually think about this as 1/2 times an x squared times a 9 minus x squared raised to the second, or raised to the 1/2 power, and to treat the product as happening with those things. Okay. So y prime still got the 1/2, but we're just going to put 1/2 and section that off, and we're going to walk through it again. First derivative of the second, x squared 1/2, 9 minus x squared to the negative 1/2, plus second times the derivative of the first, and seal. It's a lot of cleanup work. You can do it. Okay, so something that's not looking right to me. First derivative of the second, I forgot the negative 2x. I noticed that, like, this is me giving you a little bit like my brain insight. I caught myself on that only because I saw a negative in here, and I was really trying to make sure that I had a negative represented somewhere out in here, and I didn't. So I messed up my own chain rule, and fortunately, we can just kind of slide this over to the right here, put a negative 2x. But nice catch, all of you. What? Yeah, I know. One day, we'll be in a modern world when you guys can actually use manipulable paper. Me too. To be honest, when I first started teaching, I thought we would be there by now. We're not. Okay, 1/2. I am going to do a couple of things here just to clean this up. For one, actually, before I deal with any of this, I'm just going to factor out what I can. And the simplest possible thing I can factor out at the moment is just a single 2x. Because that 2x can kind of come out. It's going to multiply by the half that's already there and just give me an x. And before I do too much else, I'm going to flip the order of these two terms, I should say, around, because one of them is minus, and I want that 1 second. So I've got a 9 minus x squared to the 1/2 I'm going to write as a radical. I have a minus. I've already factored out the 2x, leaving behind an x squared in the numerator. And there's still a lingering 2 in the denominator, as well as a radical 9 minus x squared. But that was a little bit of a nice cleanup step, because now you can kind of see what you have to do. LCD of 2 root 9 minus x squared to add those two pieces, and you should. Y prime is equal to, this is going to become 2 times the quantity 9 minus x squared over 2 root 9 minus x squared. Okay, now we continue with a couple of strategies to kind of clean this up a little bit more, because we can keep going. We want to move it into a place, like you've already gone this far. Let's distribute, and I'm going to move the x to the numerator so I can keep everything in a nice rational form. 18 minus 2x squared minus 3, or x squared is minus 3x squared over 2 root 9 minus x squared. Almost there. One thing I'm going to do, I'm going to factor out a negative 3. I probably shouldn't, but I'm going to anyway. There's a weird reason why you shouldn't, but I'm going to. It has to do with symmetry. A lot of times books really like the 9 minus x squared in the denominator to match a 6 minus x squared in the numerator, so everything looks weird and symmetrical, but I hate having negative leading coefficients. So I'm going to pull the negative 3 out anyway, because it's me. Negative 3x, and I get x squared minus 6 over 2 times root 9 minus x squared. Actually, I'm pretty more sure I'm right on this, because the majority of the time what you're trying to do is look for horizontal tangents. And horizontal tangents are anywhere that the whole thing is equal to 0, and the whole thing is equal to 0 when the numerator is equal to 0. You want the numerator to be as factored as possible. Plus, we're going to be doing sign tests on the numerator. By sign tests, I mean SIGINT tests. Those things did with Manton. Okay. Having fun yet? Lots and lots and lots of algebra. This is lots of algebra, and there's more algebra coming. Okay. Chain rule says we have to do the derivative of the inner, and the derivative of the inner is a quotient, and the quotient rule is, sing it to yourself. Low, D high. I don't know. Minus high, D low. Over low, low. And that whole thing we just wrote is just simply the derivative of the inner. We still have to do the derivative of the outer, which is a function squared, which the derivative is 2 times that function, then raised to the first power. But it's good to leave it separate like that, and I would not carry that square factor, or like the power, into the individual terms and then take a derivative. I know that might be a temptation, because if you want to move that square term in and just leave them as different pieces, yeah, but then you're going to run up against having to factor things back out again that are already factored out right now. Okay, next, we got to do some cleanup. Here's how we're going to do it. And please don't be intimidated by the cleanup steps. These should be the fun parts. Let's factor something out of those two. And let's try to pull it off over until to the right side and kind of move it out of there. Actually, I'm going to move it to the front just to keep things clean. Constants, got 2 and 3. No. X's have an X and an X to the 4th. So really the only thing I can pull out is an X. And I'm going to look at that X squared over here and combine them now. Let's make it an X cubed. And let's keep that 2 with it too so that I can group that. So I've taken care of that 2 and the X squared on the right side. And we're going to draw a giant fraction bar, and now just kind of keep track of what's left in the numerator now that I pulled I just pulled an X out. Don't lose track of that you've only pulled an X out of that. So having only pulled an X out, I have a 2x cubed plus 4 minus 3x cubed, because again, I pulled an X out. So that's an X cubed. Be careful, if it's too many steps at once, backtrack and just do one thing at a time. The denominator really is encompassed by these two things, this and this. So I have an x cubed plus 2 squared times another x cubed plus 2, which gives me an x cubed plus 2 cubed. Almost there. As I have the 2x cubed minus 3x cubed, I'm just going to subtract them and get a negative x cubed, which, of course, you know me, I'm going to factor the negative out completely and make it a negative 2x cubed to give me positive x cubed minus 4 over x cubed plus 2 cubed. Still have h prime of x at each step. I prefer to keep that there. And that's done. That's about as factored as that can go. Okay. Seriously, your first derivative should just look pretty and pristine and be nicely grouped and nicely clumped together. This is going to be a very similar type of thing, so feel free to kind of zoom ahead and practice this one. Low, d high, minus high, d low, over low, low, times, then the outer would be a 3, and a 2x squared plus 1 over 3x minus 2 squared. At no point will you have to square any of these. All you're going to be doing is sort of separating that square out and just keeping them factored. So that shouldn't be a big deal. It's really not that different. You're still looking at whatever you can factor out of this side and this side. Constants, you have a 3 and a 4. X's, you have an X and nothing. The factors don't even match. So, oopsie. Your only strategy is to multiply it all out and combine like terms. So let's do that. 12x squared minus 8x minus 6x squared minus 3. And we're going to start to combine this into a single fraction bar. So then a 2x squared plus 1 squared over 3x minus 2 to the 4th power, because there are 2 of them from the first part and 2 of them from the second part. Then just clean this up a little bit more. Let's take the 3 and move it out in front, because that's where we typically see constant or coefficients. Have a 6x squared minus 8x minus 3 times a 2x squared plus 1 squared. Because whatever I say Izzy has to listen to, I'll tell you the story of running roulette. There are actually 2 games called running roulette. One of them is historical, like 15 years ago, cross-country team, where the strip mall that is at Michigan and just a little bit south of 86th Street. It's the one where there used to be a Mexican restaurant. There's used to be a fitness thing there, and just like giant shops. It's easily missable, but if you're going north on Michigan, it's the first one that appears out of that whole gamut of stuff that happens at 86th in Michigan. And we used to run alongside the strip mall. But you'd run, like the dare was to run as close as you could to the doors because you never knew what door might open and then it just takes you out, or you take the door out. This is actually more than 15 years ago. This is probably, yeah, this was junior, senior year of high school. We called it running roulette because, like, you know, you never know when you're going to shoot yourself in the head by just slamming into a door or into someone. So that's one game of running roulette. And I bring that up because you don't want to play polynomial roulette with this one. How many of you just pray that didn't factor, but you didn't actually check it? You don't know unless you check. How do you check that it factors in a very methodical and quickish way? Do you remember doing b squared minus 4ac, that part of the quadratic formula? Because if that is a perfect square, then the quadratic formula works out to become rational numbers. So if that is a perfect square, then the polynomial will factor. Did you ever know that if b squared minus 4ac is a perfect square, the polynomial factors? And if it's not a perfect square, the polynomial does not factor, at least with real coefficients. Well, no, rational coefficients. So let's just check that really quick. 64 minus 4 times 6 times negative 3. Or 64 plus 24 times 3 is 72. And really you just have to know, is 136 a perfect square? Nope, 132 and 144, but not 136. So negatory, that doesn't factor. The second running roulette, I know I told you there were two games called running roulette. The second one is a little bit more disgusting, we'll say. It's when you're running and you have gas and you need to release that gas. You are 90% sure that that will release as gas, but there's always that 10% that it's just not going to release as gas. Do you take the chance? I don't know. And for everyone to hear, for YouTube fans everywhere, no, the only ones people watch are the calculator videos. These are just like you guys, and that's it. Okay. Y equals. Before doing anything with trig, especially if you see sine and tangent in the same problem, what might you want to check for? Yeah. This is sine of 2x times sine of 2x under cosine of 2x. Which is just really cosine of 2x. I just asked you to take the derivative of cosine of 2x. Don't do low d high minus high d low over low low if you can simplify the original thing. What's the derivative of cosine of 2x? 8. Oh, you were so cool. You had it so good on the other one where you caught the chain rule problem. What's the chain rule problem here? What's the leading number that has to hit? 2. Yeah, so negative 2 sine of 2x. It's easy to miss the negative or the 2 part because you have to do the derivative of 2x before you can do the derivative of cosine. Derivative of cosine is negative sine. You get this. Okay, let's talk about number 6. You guys know that something messy is going on here because I'm multiplying sine and cosine. And this should trigger in a positive sense, not the submillennial trigger as a negative word sense, a good part of your brain to know that this is the first identity, the sine 2 theta identity. So here's how you can do it with the 1/2 thetas if that's messing you. To make it methodical and not to make it so we don't have to think about it. The identity is 2 sine 2 theta is equal to 2 sine theta cosine theta. It's really fun to think about like the tricky lumps of derivations we did with that one. We derived that from the sine double angle or sum angle identity. We did theta plus theta. And we derived that one from a picture of 2 ways with angles that we did last semester. But in any case, the part that matches, I need this theta to be the same as 1/2 x. So I'm actually just going to do a good old Mrs. Manton style let statement. Let theta equal 1/2 x. And then we're going to substitute that back into the identity everywhere. So every time there's a theta, we're just going to put 1/2 x in. Sine of 2 times 1/2 x is just sine of x. 2 is still 2, but theta is now 1/2 x, 1/2 x. Which means that this whole thing is actually equal to sine of x over 2. And all of that was just some trigonometric finagling to use that identity to rewrite f of x as 1/2 sine of x, which is ultimately a very boring derivative. 1/2 cosine x. Done. It's okay. Many of you might have done product rule on that, and I would have waited. But you don't need to. Okay. Number 7, and ones like it. I need you to see that as a nesting of 3 functions. You have the x that you're multiplying by 3, then you're taking the tangent of it, then you're cubing it. The cube happens last. And the best way to do and see this is to rewrite it as the tangent of, squared. Tangent of 3x squared. The square happens last. So first, I'd like to think about nesting functions like you are x. What is happening to you? What's your experience? What's your lived truth? You're being multiplied by 3. That's transforming you. Then you're being made the tangent of that. That's transforming it again. Then it's being squared. This is something that when we first did functions, we really tried to nail into your brains back with Chapter 3C and Algebra 2 Honors. Yeah, I know all these. All right. But I remember the function machines and all that, about how function just takes a number and changes it to another number, then changes it to another number, and then that changes it to another number. That's what's happening here. X is being multiplied by 3, being changed into another number. Then you're taking the tangent of it, it's being changed into another number. Then you're squaring it, it's being changed into another number. So keeping track of the order that's happening will help you kind of keep track of the chain rule when you're taking derivatives. H prime of x, first inner thing, the 3x. So derivative of that is 3. Then we move outwards. The derivative of tangent of something is secant squared of that something. So secant squared of 3x. And then finally, the derivative of something squared is 2 times that same something to the first power. That's a raw derivative, slight cleanup. 3 times 2 is still 6. But you really can't do anything when you're multiplying secant squared times tangent, since in both cases cosines are in the denominator. It's not considered any more simple than having sine of 3x over cosine cubed 3x. It doesn't matter. But let's just keep it in terms of secant tangent, because secant and tangent are friends. They exist in a lot of identities and a lot of derivatives and a lot of things together. Cosecant and cotangent are friends, and sine and cosine are friends. Okay, number 8. Also features a nesting of 3 functions. The difference with number 8, especially with this, is what order things are happening in. So if you are x now and you are living your truth, you're being multiplied by pi, then you're being squared, and then you're being taken the cosine of. You see the different order that happened there versus the previous one. In the previous one, the trig function happened before the exponent. Here, the exponent's happening before the trig function, and it is not creating the same result. Otherwise, those would be interchangeable, and they're not. So f prime of x equals derivative of 7x, 7, that's done, minus, still have the 3. Constant multiplier rule says we don't really even need to deal with the 3 because this whole thing is happening after. Then we're going to multiply the 3 times the derivative of pi x, which is pi. The derivative of something squared is 2 times that something to the first power. I'm trying to be careful that these actually show up as dots. Times the derivative of cosine is negative sine of that same thing that was there. So unfortunately, the only way to really clean this up is to multiply the 3 times the 2 to give me a 6, multiply the pi times the pi to give me a pi squared, have an x, then minus negative can become a positive, and then the sine of pi x squared. If you really want to be super clear about what your operations are, you can also put another set of parentheses after that sine x to kind of group it like that. Sometimes you'll see me do that just to be completely clear. For instance, on a test or quiz, I probably would do that just to be completely clear about where that square is. Okay. I believe this is the last one, and it's a doozy. You ready? First thing you can kind of predict, there's going to be absolutely no good way so really no way I'd want you to combine the sum of these two when we take the derivatives, because they're just too different from each other. So treat that as really two problems that we're going to keep completely separated. Only in the case where there's an obvious way to add them together am I going to want you to. There's not going to be an obvious way here, just being honest about that. So this is just going to be a mesh of stuff that we'll try to condense down as much as we can. Your first step really should be to take the problem and rewrite it in exponential form with all the exponents, and to overuse parentheses so you can get a clear picture of what's happening first to x, what's happening next to x. And there we go. If there was one big picture thing that I would ever want you to come and guest star and talk with Algebra 2 classes about, it's really about the order of functions, because here you can clearly see that there's a difference in what's happening. You're raising the x to the 1/3 and then you're taking the sine. Here you're taking the cosine and then you're raising it to the 1/3, and it does not create the same thing. Even if those were both sine, it's not doing the same thing. And there's a definite difference in how you take derivatives. So let's start. Derivative of x to the 1/3. 1/3 x to the negative 2/3 times the derivative of the sine of something, is the cosine of that something, plus, then we go inside, derivative of cosine of x, negative sine x. Then we go 1/3 cosine of x to the negative 2/3. In many cases, a raw derivative is going to be what's acceptable here. But I want to keep these things separated while still trying to get some semblance of order happening with this. It's just going to be, for me, about what's in the numerator denominator. The numerator for the left part of the plus sign is going to be the cosine of the cubed root of x. I'm kind of committing to writing these cubed roots in radical form because the original problem had it that way, so we'll do radical form the whole way out. 3, x to the 2/3 in radical form is the cubed root of x squared plus, kidding, we're going to make it a minus. I think you see why. Then I have a 3, nope, 3's in the denominator. Just have a sine of x over, I have a 3, and then this is going to be tricky. Cosine of raised to the 2/3. One way I can write that is the cubed root of, let's put a 3 in there, cubed root of cosine squared x. Now, under no circumstances would I really want you to add those together. You can't. I mean, you can, but that's just going to be messier. So leave it. And I want you to have a good instinct of when it's okay to leave these things. Done.